Okay, let's try to make some progress today with material. The green is an outline. I typically will give outlines for all of our material. Okay. Front and back. And then we got a white handout. Organic chemistry, chemistry of carbon. Y'all ready? Okay. Here we go. Well, shall we start with carbon? Yeah. What do we got? Let's make it a 6 here. I can put maybe one of 12 here. What is a 6? Atomic number and 12. Yeah, mass number. Subatomic particles. How many protons does the carbon have? 6 protons, right? How many electrons does carbon have? Well, that's if neutral. I mean a standard neutral carbon. This is sort of a starting point. How about neutrons? Yeah, 666 neutrons. Okay. Where does the number 12 come from?
Neutrons and the protons.
Okay, we can have maybe something like this. Do we really need to put the 6 here? No, because any carbon is 6. Usually you don't even need to show those numbers. If it wasn't 6, it wouldn't be carbon, right? Well, okay, what's the difference here? How many protons?
6.
And
7 neutrons.
okay, 7 neutrons. So 6 and 7 is 13 mass number. What's the relationship of these two? Yeah, isotopes vary by different number of neutrons. What else we got? We got what? Carbon 14?
11.
What we got? 6p, 6e, and what's that? 8? Yeah. Was there another one?
11.
Carbon 11. What do you know about carbon 11?
Radioactive.
Yeah, it's radioactive. Carbon 14 is radioactive. Okay, these 3 are your natural ones, the ones that are naturally present in nature. Okay. Carbon 12 is about 99%. 99% of the carbons in your body are carbon 12. About 1% of them in your body are carbon 13. And then a trace amount, carbon 14. Carbon 14, the dinosaurs used to date the dinosaurs, etc., because it decays over time. Once the dinosaur dies, then it's no longer replenished and it starts decaying from a baseline. Yes, you can also have carbon 11. Carbon 11 is man-made. It's not natural. You can make other isotopes synthetically. Of course, this would have, what, 5 neutrons? Yeah. Carbon 11 is important because of PET imaging. Are you familiar with PET imaging? PET imaging uses radioactive nuclides, isotopes, atoms. Atoms can be part of the molecule. Fluorine-18 is a common one for PET imaging, but more and more carbon-11 is being used. They may make it over here on Central Avenue, some to serve the hospital. I know they make it in Columbia. The problem with making it in Columbia is it has a short half-life. By the time you truck it over here from Columbia, it's kind of almost too late. Here's something from Wikipedia. Imaging of Alzheimer's. On the right is a healthy brain. On the left is Alzheimer's dementia patient, and the yellow and red, orange is indicating beta amyloid, which is basically indicator of Alzheimer's. And so you can study the progression. This scan is generated by dosing this compound here. It's a typical organic compound with some functional groups and heteroatoms, meaning non-carbons, This nitrogen has a methyl group, but the carbon is carbon 11. Okay? This compound has been synthesized somehow. The carbon 11 generates a positron, and the positron can be used to generate an image through positron emission topography or PET imaging. Okay, question?
Standard to put the number of the isotope if it's an isotope in a molecule.
If it's unique, because you don't say anything, the reader is going to just
So you
assume it's
see
just the
what-
most abundant one, like carbon, or that it's just natural. Anytime you see a carbon, you know 1% of them are C13. Okay. All right. Okay, so these two are where? The atom. There.
The nucleus.
Yeah, the nucleus, and then the electrons are, you know. Essentially, though, the outer sphere of the atom is electrons. Okay. Electrons are going to be your most important for reactivity. Typically, we will not do any nuclear chemistry in this course. Okay, so we'll just be talking about the electrons. So, I know you guys can do any of this for any element over here. For example, how many neutrons does tellurium-128 have? Well, you have to maybe do a little math, but it's 76, right? Okay. Oxygen, sulfur, selenium, tellurium. Okay, electrons. What does configuration of carbon-12 look like? Not necessarily has to be carbon-12. What we got? 1s, yeah? 2s, is that right?
2p.
I haven't had Gen Chem in a while. 2p. This is some energy here, relative energy. What we got? How many electrons we got? 6. 1, 2, 3, 4, 5, 6. Is that right? Okay. This is kind of a subshell. What's this shell called? Yes, valence shell. Right? So carbon has 4 electrons in the valence shell, and it's those 4 that we're really going to be working with. The 2 in the subshell we're never going to really work with. Okay? Just like in the nucleus, we're never going to work with. Okay? So that'll be a starting point, but usually carbon will hybridize when it bonds. So we'll have to talk about hybridization. And we will not use the ground state configuration typically. Okay, bonding. By the way, are we going along the outline?
Yes.
Protons, where are they? How many? Electron configuration. Valence electron. Types of orbitals. Okay. What's an S look like?
Here.
S is spherical. Yep. With the electrons really approaching the nucleus and actually closer to the nucleus, okay, as opposed to a p orbital, which is going to be what? More like this, and it really tails off at the nucleus. And so we'll talk about closer to the nucleus. An electron in an s orbital is going to be closer to the nucleus, right? Gen Chem? Okay, p orbital, no. And then as you go up, these can get bigger as you get a bigger shell, outer shell. This is just review, yeah? Bonding. First off, hydrogen. How many electrons does hydrogen have? Yeah, just 1. Now, what type of bonding is it going to do? What does it want to achieve through bonding?
Stability.
Hydrogen wants to achieve sort of an arrangement that looks like
Helium.
helium. How many electrons does it need to look like helium? 2. two total, one more. Just one more. I mean, we could give this one more somehow. It could pick up one more. That would have two, and we could talk about more how it resembles helium. We could also talk about charge. This would be charged. Okay? We'll do more charge in a minute. This is possible. But let's talk. But this isn't covalently bonded to anything. How can we covalently bond this? Well, what if you had another hydrogen that just had one? Well, what if they teamed up? Instead of giving this an electron, we're going to ask it to get an electron by sharing. And this guy can get an electron by sharing. They can each share, and we can make a bond that sort of ends up with the two electrons kind of sitting between the nuclei like this. And they're both kind of sharing it, and the electron cloud is sort of here. And then we can sort of call this a bond. And at this point, what I just discussed in the last 20 seconds could be the topic of an entire course. There's books this thick about the nature of the covalent bond. Okay? We're not going to dive too deep into it. Two electrons being shared between two nuclei. Is that reasonable? Okay. What type of orbital? Okay, there's lots to it. And we can depict this here. Instead of that, we can depict it as what? The little dash line, which indicates what?
Covalent bond.
A two-electron covalent bond. So there you go. That's H bonded to H, covalently. Each nuclei, you get to say, kind of owns two electrons through sharing. Not satisfied with that? Check that book out about that thick. Okay? There's a lot there. It's a lot of math. But that's enough to get us going. Okay. In the end, how many bonds does hydrogen need to make to become like the noble gas configuration? One bond, because each bond it makes, it gets to share another electron. Okay? One bond, you get to share one more. So now the hydrogen has two electrons around it, like helium, and we call that a duet for hydrogen. Okay? Now for carbon, on the other hand, and I'm going to do this with sort of carbon, nitrogen, oxygen, etc., and then come down and leave some room, okay? Some space. I'll come up here and then we'll erase it. Carbon, how many electrons are we starting with? Valence electrons, because those are the ones that are involved with bonding. Four. 1, 2, 3, 4. We only had one there. Okay. What does carbon want to become like to be most stable, etc.? Neon. Neon, which has a total of 8, right? So how many more does carbon need? 4. How many bonds does it thus need to make? 4. Yes, each bond you get an electron. We can bond this to something. Let's say we bond it to a hydrogen, which has one electron. So we bring in the hydrogen with its electron. I'm going to call that electron an X. So the X came from the H, the dot came from the carbon. Bring in another hydrogen and its electron. Bring in another hydrogen and its electron. Bring in another hydrogen and its electron. And so now we have something that looks like this. I should have started higher. I'm going to write something down here. Hydrogen makes one bond. If you look at sharing, you get to count of both. Hydrogen has 2 electrons. Duet is happy. How many does carbon have? You get to count all the bonding, sharing. It has 2, 4, 6, 8. So you get to double count. So now carbon has 8. We call that octet, right? Carbon has achieved octet. Carbon thus needs to make 4 bonds. This is methane. Okay? That's why it's CH4 and not like CH3. CH3 would not be appropriate. It would not achieve an octet. Standard bonding for carbon. 4 bonds. 0 lone pairs. Let's look at nitrogen, okay? Chemistry of carbon, but don't be misled. These other guys, nitrogen, oxygen, your halogens, very important, okay? Phosphorus, sulfur, okay? Even as we go along, we'll see other things that are important in chemistry. Boron, aluminum, magnesium, okay? Palladium, huge in organic chemistry. There's lots of other players, so we have to be familiar with them as well. Nitrogen, how many valence electrons? 5, yeah? I'm going to go around and then I'm going to team one up. There's your 5 valence electrons. How many bonds do we need to make to get an octet? So they all want to get the octet, be like neon. Yeah. We can bring in an H with its electron. By the way, could we bring in anything else? Yes, we could bring in a carbon and have one of its electrons bonded here, but then the carbon would have 3 other electrons. I'm just keeping it simple. Is nitrogen now good? How many electrons around it? 8. 2, that's 2. 2, 4, 6, 8. Okay. This can be shown as this. And this is a good old molecule called what? Ammonia. It's a gas. Well, methane's also a gas. Common bonding for nitrogen. 3 bonds, 1 lone pair. This is standard bonding for these elements we're going to do. Okay. Does this mean it can not bond other ways? Will you ever see a nitrogen with 4 bonds? Yeah, we will. But it won't be standard. And if it ain't standard, it's probably going to have a charge. Decharge it a little bit, okay? This is standard. No charge. Now there is an exception to this. I could show you a nitrogen that was not standard and that did not have a charge. That would be an exception, unusual. Typically, if it's not standard, it will have a charge. Oxygen. How many valence electrons? 6. Okay, 4. Then start teaming up. Why do I start teaming up after going just 4? Ground state configuration of carbon. How many valence orbitals were there?
2.
I've already wasted.
2.
Not 2, not for me. 4, right? There's the 2s, and then the 2 p's, and there's 3 of those. 3 plus 1 is 4. Let me ask you again. How many valence orbitals in the ground state of carbon? Should have been easy, guys. Okay? That's the detail. When you look at things, don't just look. Ask questions. What could be asked? What do I need to know here? We identified as valence. Well, then, what is there at the valence? Okay? There's 4 orbitals. That's why we're doing 4, because we got 4 places to put electrons. Then we start teaming up. So that's where that comes from. Okay, how many bonds we need to make? 2. We can bring in H's. What do we have? Right? Water. Okay? 2 lone pairs. Standard bonding for water. I mean, not water, but oxygen. 2 bonds and 2 lone pairs. Oxygen. All this because these guys want to become like neon, and this is how they do it. Standard bonding. What's next? Fluorine. 1, 2, 3, 4, 5, 6, 7. How many bonds we need to make? 1. We can make HF. Okay. 3 lone pairs. Now, a lot of times you see these guys drawn, you may not see the lone pairs shown. Either someone's just trying to be short about it, being lazy, or they're using a drawing program. The drawing program wouldn't be able to draw a lone pair, et cetera, et cetera. Okay? Does that mean it's not there? No, it's there. Because if it wasn't there, there'd be a charge there, et cetera. Okay? And if we do something kind of officially, we definitely want to have the lone pairs there. Hydrofluoric acid or hydrogen fluoride. Standard bonding for fluorine, 1 bond, 3 lone pairs. Okay. What's standard bonding for bromine? Same thing. What's standard bonding for selenium? Okay. Well, hopefully you said whatever's there, because it's standard bonding for silicon. Yeah. Okay. The exception is once you come down, now you're in the third shell, and now you have d orbitals. And because of d orbitals, these things down here can bond in some other ways. Okay? They do bond like this, but they can also bond other ways using d orbitals. So you will see some fancy exceptions. Carbon, 4 bonds, 8 electrons max, because it ain't got no more orbitals. Silicon, though, you can have more electrons around it. It can expand its octet. Okay? You'll also see some fancy bonding for maybe like iodine. Okay. This is most common. There are exceptions below. Okay, whenever I say or start looking at my paper, it's a good time to throw out questions.
So do you think carbon became the essential part of life because it was a smaller, more stable atom than silicon?
Well, I'll give you the answer, but I can't tell you the why as easily. The thing about carbon is it's very willing to bond to lots of other things. It's a good friend. Okay, it makes strong bonds to itself, where an oxygen bond is not as strong. Fluorine bond not as strong. Those things don't like to bond because they're more greedy and the same thing with silicon. You don't often see lots of silicons bonded to each other. Now, what's the deep answer? Why does carbon like to bond to itself? That's where it kind of becomes this thing. That's why there's so many types of carbon compounds. It's just such a friendly bonder. Probably because it's just the right mix of electronegativity. It's not too electronegative, but it's also not just a pushover. And so it's a good friend, but it makes strong bonds too. So that's sort of an explanation, but not that scientific. I prefer non-scientific explanation sometimes anyway. Well, we erased that. Hopefully that was good. Octet rule, right? Except for hydrogen. There, that's the duet. Duet rule. That's not optimal. Mission. Let's see where we're at. Did we cover A? Okay, we're going to show structures. Anytime we show structures, we're going to be showing Lewis structures. That's basically what a structure is for us today. Show the bonds and the lone pairs. I showed you the Lewis structure of water up there. Okay, just a definition. He was the one that maybe wrote that thick book about the chemical bond. We talked about expanding the octet. Let's do some more structures. B, how about CH4O? Can we put together a structure a little more complex? At least today. By the time you get over to organic 2, this is going to be like, what? Okay, but we're going to start, and we're going to do it very systematically. That is, I'm going to show you an approach that will then be useful for applying to other. Okay? All right, CH4O. I would start by getting here. Hydrogen only makes 1 bond, so it's going to be on the periphery. You never want to have a hydrogen in the middle and multiple things bonded to it, right? Okay. C. So, if you think about it, the C and the O must be bonded together. That's a good place to start. Is bond your carbons and your heavy atoms. Okay. First off, here's a more important place to start. How many valence electrons do we have? Because when you show a Lewis structure, you need to show all valence electrons. That's what we did with water. How many are we dealing with? Carbon's 4. Each H is 1, so that's 4 more 8. Oxygen is What's that, 14? Okay, when we get done, we should have 14 valence electrons. All right, C to O. There we go. Next, I would recommend then bringing in your hydrogens and bonding them to carbon. Okay? It's just more common arrangement, and it's just going to work better, and so that's the recommendation to do first. Fill the valence of carbon. So how many H's do we put around carbon? 3. Now, see if we can get this. Where do you want to put the other H? Well, you can't put any more around carbon. Carbon standard bonding is what? 4 bonds, no lone pairs. There you go. Well, what's here? You got to put the H here. Okay? Systematically, it will just kind of fall into place. Follow. That's not always going to fall into place until you get the hang of it. Well, how many valence electrons up there? If you count them, there's only 10. Where do the other 4 go? Yes, there's 2 lone pairs. Standard bonding. There you go. There's a good low structure. CH4. By the way, that's just pure formula. A lot of times you'll see formulas sort of with more information in them. Like, that's the same formula, but the person is giving you a little bit of information. It's a CH3OH. Okay? A lot of times you'll see like this. Formally, ideally, it's CH and then alphabetical. But you get the point there. Okay? It's indicated. This is methanol. It's basically a methyl OH. CH3 is a methyl. We'll learn nomenclature. By the way, nomenclature, if you see in the syllabus, there's some things that are by video only. Okay? The lecture video posted on YouTube. There's also a collection of videos for you. I believe nomenclature, alkane nomenclature is there. IR is there. I sent you by email. Okay, mentioned that. And there's also some lab videos there, demos. These are hopefully referred to let you know they're there, but you should also be looking. Also, since they're there and you want to maybe get a jump on things, I will try to get you the handout sooner than later. But usually when you look at these lecture videos, you want to have the handout with you, because I'm just covering the handout. Okay? Methanol, common alcohol. Yay? How about another one? C2H6O. And advanced electrons. 4 times 2 is 8. 6 more is 14. What do we got? 20 valence electrons. Okay. Valence electrons. 20. Let's see. How do you want to put the non-hydrogens together? What about this? Carbon, carbon, O. Let's see how this, we got 6 H's. Let's see, 1, 2, 3, 4, 5. Okay, on carbons first. And lo and behold, where do you want to put the other one? Here. If you look at it, that's probably only 16 valence electrons. Where do you want to put the other 4? Right there. There you go. There's a good Lewis structure. 2 carbon fragment is an ethyl group. Ethyl alcohol. Ethanol. Anybody familiar with ethanol? Yes, you can partake in a little ethanol. Please do not drink methanol. You'll be blind. Okay. Moonshiners who try to make their own alcohol end up with a lot of ethanol in their whiskey or whatnot, and especially in the olden days, their eyesight would. But why? Why does methanol cause you to go blind? Well, it gets oxidized. Standard organic chemistry reaction. Oxidized to what? Well, an aldehyde, a standard organic molecule. And then how does the aldehyde react? Well, it reacts with proteins in the eyes. How? This is all organic chemistry. Reacts with the proteins and they're no good anymore. Ethanol. Could we put this together another way, though?
Yeah.
Yeah, a functional group. But instead of doing CCO, what about if we had done COC? What about that? How many H's we got? 6?
Still 6.
There we go, there's a 6, and then 2 lone pairs. There you go, there's another good structure. These are 2 different compounds. Yes, one's an alcohol. By the way, there's a list of functional groups in the handout. We'll definitely be looking at those by first thing on Friday. Please be looking at those. Reading in your textbook about functional groups. I'll bet you a nice steak dinner or more that your textbook has functional groups in it, no matter what textbook you have chosen to use.
What did you say the name of this compound was?
Do I?
What did you say the name of this compound was?
I don't know that I did. That's ethanol. This functional group, an oxygen bonded to 2 carbons, is an ether. Oxygen bonded to 1 carbon and with an H, that's an alcohol. This is an ether. I'm just going to say an ether. That's kind of a generic description. You have multiple types of ethers. That is dimethyl, because it's 2-methyl, dimethyl ether. 2 different compounds. That's a gas at room temperature. This is a liquid at room temperature. Different properties. What's the relationship between these 2?
Constitutional isomers.
Constitutional isomers. What's the definition of that? Same formula. Isomers have same formula.
Different connectivity.
They have different connectivity. The atoms are connected differently. And connected means it's more than just projected. You saw 2 people and one had their arm this way and one had their arm that way. They have the same connectivity. The arm is connected to the shoulder. It's just projected differently. So we'll get to that. These are connected differently. Obviously here the oxygen is connected to 2 carbons, where here it ain't. Constitutional isomers. Okay, these 2 compounds have no degrees of unsaturation. Degrees of unsaturation is in the other handout. We'll definitely get it on Friday morning. It's very important, though, that you have looked ahead, so you're not hearing this for the first time, and you're able to hear things and fill in the gaps and come to class with questions, and etc. Okay, let's try another one. CH2O. How many valence electrons?
12.
We got 4, 6, 12, yeah? CO, H, looks like I need another H or something. What's going on here?
You need a double bond to the O.
Okay, yes, but let's approach it systematically. How many electrons I got there? 2, 4, 6. I got to put 6 more. Okay. At this point, we're going to put them up there not as bonds, but as lone pairs. And we're going to now, using lone pairs, make these guys happy. Which one do we need to make happy first? Which one?
Oxygen.
Oxygen. Oxygen is more electronegative. It's more demanding of these electrons, right? Electronegative. It likes electrons. If it likes electrons and you start giving them a carbon, what's the oxygen going to do? It's going to hunt you down. Okay? Let's fill the oxygen first. How many lone pairs you want to put around oxygen?
2.
3. Because we want oxygen to have an octet. Does it now have an octet? How many around oxygen? 2, 4, 6, 8. Okay? Now, is that standard bonding? No. But we ain't done yet. Does carbon have an octet? No, there's only 6. What can we do? How about this? Now we're good. No, we only got 12. And 12 is up there. You don't have any more. How can we get carbon in octet? We're going to ask oxygen. We know you're greedy. But we need to make sure everybody's happy here if we're going to have a good structure and, pass the test. We're going to ask oxygen to share, and we're going to take these electrons, and we're doing this on the board. This is our process. We're going to take this and move them in here. And this is a mechanism arrow. This has got to mean something to us. This means that the lone pair is moving in to make a bond between the oxygen and carbon. And now we're going to show the result of that arrow movement. Okay? And we're going to ask, what does arrow mean? Well, it means that we're making a bond now. And now we're going to draw the result. So now instead of one bond between the oxygen, we have two bonds between the oxygen. How many lone pairs on the oxygen? Two. Why not three? Because the other one is now a bond. It moved in. Now those two electrons are a bond. And we got the H's here. And we're not worried about bond angles yet. And there we go. Now do we have a good structure? Does carbon have an octet? Yes. 2, 4, 6, 8. It's a double bond, but it's two electrons, 2 electrons. You get to count them both. Does oxygen have an octet? 2, 4, 6, 8. Yes. Here we go. Which structure do you like best?
The second
This one. Everything has an octet. That's a big factor. Okay? Now we have typical bonding. Let me end on this since we have the structure. This is not typical bonding. We said probably charge. What's the charge of this? I'll ask you, let you do this, and we'll talk about it Friday. So let me see. Both of these atoms are charged. What's the charge of those atoms?
Well,
Other thing on Friday. Other thing. What's the relationship between these two structures? These are resonance structures. These are actually the same compound. All we did was move electrons. Just like if I stood here like this and said, okay, what's the relationship between me like this and me like that? Well, it's me. I just have different organization of my arm. That's one compound up there. Resonance structure. We'll develop that idea as we move forward. Okay. Looks like we're out of time. Have a good day, guys.
All right, then. Yeah, I gotta run all the way off campus.